So we're going to start with spontaneous. So if we have a spontaneous, I'll write this word a lot today, reaction. This is one that once it's started, it will go all the way to forming the product. So once all the reactants are used up, except the one in excess, it will make products. And so they have a special term, the science community, or phrase, I should say, that this is the type of reaction that goes to completion. And my example for a spontaneous reaction would be if you lit a piece of paper on fire. It's going to keep burning until all of the paper has turned into ash, CO2 vapor, H2O vapor. So this is an example of spontaneous reaction. Then we have a non-spontaneous category. And as you could probably assume, this does not happen at all. So if I had a cup of water and threw a piece of aluminum in that and told it to react, it wouldn't do anything. It would just get wet. So this is an example of mixing two things together that will not make a reaction, therefore is non-spontaneous. Then we have this term equilibrium. And so, of course, equilibrium, we think of the word equal. And so what this defines is a point in the reaction where, sure, it starts, but it starts to slow down before we've completed it. And so it's really the forward reaction changes and the what we call the reverse reaction. These are both happening at the same exact rate. And so we consider both the forward, so the reactants turning into the products, which is forward, the products turning into the reactants would be the reverse reaction. Those are both spontaneous at equilibrium. They just are happening at the exact same rate. Any questions here? Yeah, go ahead. So a lot of times we talk about like acid-base reactions. So you can push them past the equilibrium where like the acid content's higher than the base or vice versa. But if you have equal parts of the thing, it's as if they're creating both the basic and acidic compounds at the same, so you have a nice like even amount of both what you started with and what you're trying to make. I know it's kind of an odd concept. So for example, if you put like ions into water or like an ionic salt, so NaCl, the forward reaction would be like the separation, you'd form Na plus and Cl minus. The reverse of that reaction would take those and putting them back into the compound of NaCl. So we start with NaCl, the products are Na plus Cl minus. The reverse of that is starting with Na plus Cl minus and creating NaCl. What? Exactly. Exactly. It's just flipped. Any other questions? Okay, awesome. All right, so we're going to break down spontaneous reactions then. And so we already know one of these terms. So for a reaction to be spontaneous, there's a balance between our enthalpy, which you guys know as, oops, as I spell it wrong, as our heat of reaction, or delta H. That's our enthalpy. So this is what we've been talking about for quite some time now. We describe our heat of reaction as exothermic or endothermic types of reactions. And so this all has to do with their delta H values. And the other term is going to be entropy. And so entropy gets a delta S as its representation. So again, reminding you guys what enthalpy is. Enthalpy is the heat content of the system. So heat being the key word here, heat of reaction. And so this is the amount of energy associated with heat energy. And so nature likes a decrease in this value. So what sign of delta H is that? Negative. So nature likes negative delta H in enthalpy. And so we're going to use this word again. It likes when reactions have a net decrease in potential energy. So if we're decreasing the potential energy, I'll draw a PE diagram up here real quick. What type of reaction is this? Exothermic. So nature likes exothermic reactions. These are the type of reactions that give off heat to its surroundings. So the potential energy of the reaction decreases, so it gives off heat. This would be an example of our water, of our calorimeter. When it heats up, it's because of an exothermic reaction. Nature likes that. Endothermic reactions, if we think about why those are not good, it's because they need a constant input of energy. Nature is like chemistry students. They don't want to have to put in more work than they need to. All right. Next term here, let's talk about entropy. So this describes the randomness of a system, if it's ordered versus disordered. And so nature likes an increase in entropy. So it likes disorder. And so as entropy increases, it increases as temperature increases, which this should start to make sense to us because we can make the connection between states of matter. So if you think about molecules in a solid state versus molecules in a gas state, what do you think has more disorder? Gas. So gas phase, because they are moving, they're moving quickly, we tend to turn things from a solid to a liquid to a gas with an increase of temperature. Increased temperature, increased disorder, increased entropy. So the gas phase has the most. What do you think has the least then? Solid. So this means that we're going to give this the term increase in phase. Nature likes when we turn things from solids to liquids to gases. So I'm going to give you a little rank right here. I'm increasing delta S. Solid is less than liquid, which is less than aqueous phase, which is less than gas. And so the reason why aqueous has more disorder is because a liquid could be just like a liquid compound. We could just have concentrated something. But the second that we make it aqueous, it gives us the opportunity to form ions, which are even more separated and more disordered. But this is just the generic kind of trend here. Okay, so if we look at this first example here, we are starting with a solid and a gas, but we are converting everything into some sort of gas. Because there is a solid that ends up being a gas, this is an increase of entropy, an increase of disorder. So we always compare the states of the reactants to the states of the products. Any questions about that here? So we're just strictly looking at the states of matter. All right. So in order for a reaction to be spontaneous, both of our factors have to be favorable. And what I mean by factors, I mean delta H and delta S. And so we have to think about what are those favorable, what are the signs of those favorable things. And so if we're just looking at this generic reaction, I think it's super easy to look at enthalpy or delta H, because what sign is it supposed to be favorable? Negative. Well, you can just look at the value. We have a negative delta H, which means favored. That's good. And what we just went over in the example before was looking at the change between a solid and a gas going to a gas. So we call this an increase in phase. which is favorable. So this is just how to determine generically looking at an equation to see if it would happen spontaneously or not. Yes. That's a good question. Font must have got weird. Nice attention to detail, Owen. Love it. All right. So if both factors are favored, what is it, spontaneous or non-spontaneous? Spontaneous, because both are favored. Not only is this type of reaction spontaneous, but it's spontaneous at all temperatures, and we'll discuss why this is. Oh, I do want to say, this favorable, well, actually, we'll talk about that later. We'll come back. Okay, so now we're going to talk about being non-spontaneous. And this is when both factors are unfavored. So, like I said, super easy. Look at delta H. Is that favorable or unfavorable? Positive delta H equals unfavorable. Now, what do we notice about the phases in our reaction here? They're all gases. So, if you are working all in the same phase, how do you think we compare? Any ideas? The moles. So if we have 3 moles, so remember this is a generic 1 in front of that N2, we don't write it. So if we have 3 moles gas on the reactants, that is turning into 2 moles gas on the products, do you think we're getting more or less disordered? Less. When you decrease in moles, you decrease the disorder. So it becomes more ordered. So this is a decrease in disorder because produce less moles of gas. Because if you have a solid, you can't just compare the moles. Like it just automatically trumps if you have a phase that's not gas. Yes. Okay. Any other questions? All right. So now we're going to talk about when things aren't as straightforward, because we talked about when both of our phases are favored or factors are favored, both of our factors are unfavored. Now we're going to talk about when they're one or the other. So if we have enthalpy that is favored, but our entropy is not favored, this means that only at certain temperatures it will be spontaneous, and this is at low temperatures. And so we're going to practice identifying if enthalpy or entropy is favored again. I have a negative delta H. Is that favored or unfavored? Favored. What about my moles of gas? Exactly. So what is that, favored or unfavored? All right. So enthalpy favored, entropy unfavored. So this will happen at low temps. We're going to dig into the mathematical equation to show why that is. All right. So then we're going to look at the reverse. If our enthalpy is unfavored, but we have a favored entropy, as you guys could probably assume, this is going to be spontaneous at high temperatures. So quick check, delta H has a positive sign. Favored or unfavored? Unfavored. And then if we look at the reaction now, we are going from a solid to everything in the aqueous phase. So I'm going to write a note because solid is our, let's see, more ordered. Oh my gosh. Then aqueous, delta S decreases, or sorry, increases and is favorable. All right, any questions on kind of this breakdown, introduction to entropy? Okay, we're gonna now assign math to it. So we have this term called Gibbs free energy. And what this is defined as is the energy available. Available. IBLE, ABLE, ABLE. I don't know. Spelling's not my forte, guys. So the energy available to do work in a reaction. So this is in a system, is kind of the energy that's hanging around out there after things are going on. So like nature really likes when there's low free energy. So when the energy has a place to be. And so an example of this would be, let's say you guys are mowing the lawn. As you're going along, you are starting to decrease your energy, leaving you with less and less to do work. This is because you're expending your potential energy that you've stored. So if you are decreasing in potential energy, what type of reaction? Exothermic. This is favored. Now, because you're breaking down your potential energy, that means you're giving off kinetic. And if you give off kinetic, your temperature starts to rise. If you raise your temperature, what happens to entropy? More disorder. So you increase in entropy with an increase in temperature, which is also favored. I just want to tell you guys that nature really likes when you guys mow the lawn. All right, so we have a way that we can relate our change in enthalpy, delta H, to our change in entropy, our delta S, and this is called Gibbs free energy. And so Gibbs free energy is delta G. So the equation that we're going to use is delta G is equal to delta H minus T delta S. What do you guys think T stands for? Exactly. So if we want less free energy, the sign associated with delta G is negative. So to be spontaneous, we want a negative delta G value. This means it will be spontaneous. And so we'll talk about mathematically how that ends up coming out. So delta H is negative. That's favored. We want exothermic processes. Then we're going to treat this T delta S kind of as one term. If that is positive, likely that means an increase of entropy. So both of these things are favored. Our reaction goes to completion. And it is spontaneous at all temperatures. So now we're going to associate this with the equation. So if we break down delta G is equal to delta H minus T delta S. We know we want the overall charge of delta G to be negative. We said that delta H is negative, and we are subtracting a positive term. So the reason why this is always spontaneous is if you start with a negative number and you subtract more, it's just going to get more negative. This is why it doesn't matter what temp it's going to be at. Does that make sense how I'm explaining this? Okay. All right, so the next one here. What if you have a negative delta H and a negative T delta S? Well, this is when our reaction is spontaneous at low temperatures. But because we're not completing our reaction, there's a point where our forward and reverse reactions can happen at the same rate. So it is possible for this type of reaction to reach equilibrium. And so I want to show you guys why it's spontaneous at low temperatures mathematically. So again, we're wanting this negative here. We have a negative delta H. Now, if we're subtracting, I'm gonna put this here, a negative term, what are we actually doing? We're actually adding, which means our negative delta H becomes more and more positive as this term increases. So if we increase our temperature, we become more and more positive. So what's favored is a decrease in temp so that we make the little bit that we're adding smaller and smaller and smaller. Okay, next scenario, we have a positive delta H and we have a positive delta S, T delta S. And so the reaction is going to now be spontaneous at high temperatures. And can also reach equilibrium. So looking at this similarly, but in a different way. Wanting that negative. Now we have a positive term for delta H. So if we think about changing the temperature here, we want our delta S times delta T term to start to become larger than our initial delta H, because if we have a larger number that we subtract, we become negative. So this is why we want an increase in temperature to make this term be larger than this one, therefore becoming negative. All right, and then lastly, if we have delta H that is positive and then negative associated with delta S, then our reaction will never be spontaneous. And also never reach equilibrium. So it never does anything. And so thinking about that, delta G is equal to delta H minus T delta S. If we have a positive term here, and we're subtracting a negative term, we're actually adding, right? So that means no matter what our temp is, if we're always adding more to an already positive number, we're never going to be negative. Any questions on this stuff? Okay, let's do some actual examples. Okay. All right, so we are going to calculate our delta G. And so we have tables that tell us our delta H. I'm telling you the delta S of this reaction, but typically those aren't in a table. But we do almost everything at this 25 degrees Celsius. And so one thing, if we look at units, what do we notice about our entropy term? It's in Kelvin. So we need to make sure to always convert to Kelvin. So I just wanted to make that note here. Okay, so we're going to determine if this reaction is spontaneous or not. So if we have our delta G is equal to delta H minus T delta S. I'm going to define my terms. Delta H is equal to, well, that is defined for us in the reaction as negative 30 kilojoules. Our delta S was given to us as negative 0.010 kilojoules per Kelvin. And as we just said, our temperature, which is given as 25 degrees Celsius, then has to be converted. And so that equation is Kelvin is equal to your degrees Celsius, which is 25 degrees, plus 273. So that gives us 298K. So we are going to be using this 298K pretty much all the time for Gibbs free energy, because this is just declared as standard temp. So this is where all these values were established, was at this temperature for delta H and delta S. Okay, so is this reaction spontaneous? So if we plug everything in, that means we have negative 30 minus 298 times negative 0.010 kilojoules per Kelvin. Do some magic calculator work, we get negative 27 kilojoules. Is it spontaneous or not spontaneous? Spontaneous because delta G is negative. Any questions about this? Julio. All right, so sometimes we are able to calculate the entropy for the reaction. And so we solve for delta S instead. And so this delta G, that is given to us in the same table that we can look up delta H. That's posted on Google Classroom for you guys with today's post. So unfortunately, I'm sorry, blue packets fail you. You'll have to look online for them. I know, I can't believe it either. So you can look these things up on the table, but we're gonna solve for delta S here. So first thing we're gonna do is rearrange the equation solving for delta S. So we have delta G is equal to delta H minus T delta S. I'm going to circle the term I'm solving for just to keep track of it. We're going to add T delta S to both sides. Then our new equation is going to be delta G plus T delta S is equal to delta H. Still looking for that delta S. So the next part we do is subtract delta G. We get, I'm going to move this, well, whatever. We get T delta S is equal to delta H minus delta G. And lastly, we have to divide by T, giving us our final equation. Delta S is equal to delta H minus delta G over T. All right. So now, last thing we have to do, plug in our numbers. So our delta H, I think I forgot to give that to you guys, but you could look that up. Delta H is equal to negative 110 kilojoules. So we have that term. We have delta G and we have our 25 degrees temperature here. So if we plug everything in, delta S is equal to negative 110 kilojoules minus a negative 137, all divided by 298, because we have to remember to convert to Kelvin. It's always in Kelvin. Delta S is then going to be equal to positive 0.0906 kilojoules per Kelvin. Is this a favored or unfavored entropy? Favored. Positive S's are favored. I'm just testing you guys as we go. All right. Exactly. Okay, so now this is kind of a two-parter here. We're going to talk about, so equilibrium. When these it's a perfect balance between forward and reverse reactions. We define equilibrium when delta G is equal to 0. So we're actually going to be setting our reaction equal to 0, solving for temperature. And the temperature that comes out is when our reaction becomes spontaneous, meaning when we start producing more products than reactants. And so we're going to determine this for HI. And so like I said, it's a two-parter because we don't have a booklet or a table to look up delta S. So we first are going to calculate delta S at standard temp. Then we're going to use that delta S in our equation. So I'll break this thing down one at a time, but I want to give us a couple things here. I looked up our delta H, which is equal to a positive 26 kilojoules. And we have a delta G, which is equal to positive 2 kilojoules. So first, we are going to determine delta S. And so we just wrote that equation up above here. So I'm going to copy that down. Delta S is equal to delta H minus delta G over T. So if we plug in everything, we've got a positive 26 kilojoules minus a positive 2. All divided by, we're keeping our 298. And I'm going to actually write a note here, and you guys can too. Oops, I should use a bigger. I'm using 298 because it's defined as standard temp. And so I'm not going to keep writing this, but again, standard temp, that's when these delta H and delta G values were calculated. So because these are both dependent on 298, we're still going to use that for delta S. So we won't change the degrees unless the problem states differently. Okay, so we are going to end up getting, that was a really bad delta. Sorry. Delta S is equal to 0.0805 kilojoules per Kelvin. And I forgot my E over there. There we go. Okay. Next, we need to solve for T when delta G is set to 0. So our new equation here is going to be 0 is equal to delta H minus T delta S. So we're just replacing that delta G with a 0. And then we have to solve for T. So we don't like negative terms. We're going to add it to the other side. That gives us T delta S is equal to delta H. And now we're just going to divide both things by delta S, giving us that T is equal to delta H divided by delta S. So our last thing we have to do now is plug in the delta H I looked up, positive 26 kilojoules. And we're going to divide that by the entropy we calculated, which is 0.0805 kilojoules per Kelvin. And so what we get is a temperature of 323 Kelvin. So what this means is at temps higher than 323 Kelvin, reaction, I abbreviate RXN, is spontaneous. All right. Any questions about Gibbs free energy? Sweetness. Okay.